Hey guys, tonight we're going to dive into one of the ocean's most invisible yet powerful secrets, something so fundamental that it shapes every single drop of water in our seas, yet remains completely hidden from view. You're about to discover the ocean's secret walls, temperature boundaries so precise they create entirely separate underwater worlds. And honestly, if you tried to swim through some of these layers without proper equipment, the temperature shock alone would probably send you straight back to the surface, gasping like a confused penguin. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment letting me know where you're listening from and what time it is there. I always love seeing how this underwater journey connects people from different corners of the world. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You find yourself floating just beneath the surface of a seemingly uniform ocean, the water around you appearing as one continuous blue expanse. But as you begin your descent, something remarkable starts to happen. The water that felt comfortably warm against your skin suddenly shifts, not gradually like stepping into a cool room, but abruptly as if you've passed through an invisible curtain hanging in the sea. This is your first encounter with a thermocline, one of nature's most precise architectural features. You've just crossed through what scientists call a temperature boundary, and the water around you has dropped several degrees in the span of just a few feet. It's like discovering that the ocean has floors, invisible floors made not of rock or sand, but of temperature itself. As you hover at this boundary, you notice something fascinating. The water above shimmers slightly differently than the water below, creating a subtle visual distortion that makes the boundary visible if you know exactly where to look. This isn't your imagination, it's physics in action. Water of different temperatures has different densities, and when they meet, they create a lens effect, bending light just enough to reveal their presence. You reach out your hand and move it up and down across this invisible line. Above, the water feels like a warm bath, welcoming and familiar. Below, it's noticeably cooler, carrying with it a different quality, almost a different personality. The contrast is so sharp you could practically use it as a thermometer. Marine biologists have discovered that many sea creatures treat these boundaries as if they were solid walls. Fish that live in the warm upper layer rarely venture into the cooler depths below, not because they can't physically cross, but because their entire physiology is adapted to their specific temperature zone. It's as if the ocean has invisible apartment buildings, with each species living on its designated floor. Researchers still argue about exactly how many of these distinct temperature layers exist in any given part of the ocean. Some areas have just 2 or 3 clear boundaries, while others stack up like a temperature layer cake with dozens of distinct zones. What they all agree on is that these boundaries are far more stable and long-lasting than anyone initially expected. You notice a school of small silverfish swimming in perfect formation just above the boundary where you float. They approach the cooler water below, and you watch as the entire group suddenly pivots, as if they've hit an invisible wall. Not a single fish ventures into the cooler layer. It's like watching someone walk confidently toward what appears to be an open doorway, only to bump into spotlessly clean glass. The water around you holds more than just temperature differences. Each layer carries its own chemistry, its own dissolved gases, its own microscopic life forms. You're not just crossing a temperature boundary, you're traveling between completely different aquatic ecosystems that exist one on top of the other. separated by nothing more than a few degrees of warmth. As you continue floating at this invisible intersection, you begin to understand that the ocean isn't the uniform blue wilderness it appears to be from the surface. It's a complex, layered world with as much vertical structure as any city skyline, except these buildings are made of water itself, and their floors are invisible walls that have been shaping marine life for millions of years. You decide to investigate this invisible architecture more closely, and as you do, the physics behind these underwater walls begins to reveal itself with surprising precision. The boundary you've discovered isn't random or chaotic. It's the result of fundamental laws that govern how water behaves when it carries different amounts of heat energy within its molecular structure. As you descend further, you encounter the main thermocline, the ocean's most dramatic temperature boundary. Here, the water drops from a comfortable 25 degrees Celsius to a chilling 4 degrees in less than 100 meters of depth. It's like riding an elevator through different climate zones, except the elevator is made of water and the climate zones are stacked vertically in the sea. The precision of this layering becomes even more remarkable when you understand what creates it. Sunlight penetrates only the uppermost layers of the ocean, warming the surface water like a giant solar collector. But water is a terrible conductor of heat, so instead of mixing thoroughly, the warm water simply floats on top of the cooler, denser water below, creating these distinct thermal layers that can persist for months or even years. You notice that the boundary beneath you isn't perfectly flat. It undulates gently, rising and falling like an underwater landscape made of temperature itself. Ocean currents push against these thermal layers, causing them to bend and flex, but remarkably, they rarely break. It's as if the ocean has invisible topography, complete with hills and valleys that exist purely in the realm of temperature. Scientists have discovered that these thermoclines are far more complex than simple warm on top, cold on bottom arrangements. Some regions develop multiple thermoclines, creating what researchers playfully call thermal staircases. You might encounter a warm layer, then a cool one, then another warm layer, each maintained by different current systems and heating patterns that interact in ways oceanographers are still working to fully understand. The density differences that create these boundaries are subtle but incredibly powerful. Warm water is only slightly less dense than cool water, a difference so small you'd need sensitive instruments to measure it directly. Yet this tiny variation in density is enough to create barriers that separate entire oceanic ecosystems and influence global climate patterns. As you move along the thermocline, you observe how it interacts with the ocean's chemistry. The warm upper layer holds less dissolved oxygen than the cooler water below, creating not just a temperature boundary, but a chemical one as well. Some areas develop what scientists call oxygen minimum zones, layers where marine life must cope with dramatically reduced oxygen levels, like underwater altitude sickness. Researchers still argue about whether these thermoclines are becoming stronger or weaker due to climate change. Some evidence suggests that warming surface temperatures are making the boundaries more pronounced, while other data indicates that changing weather patterns might be disrupting these ancient layered structures. You notice something peculiar about the water's clarity at different levels. The warm surface water often appears slightly hazier, filled with microscopic plant life that thrives in the sunlit zone. But as you cross into the cooler thermocline, the water becomes remarkably clear, almost gin-like in its transparency. It's as if you've moved from a bustling city street into a quiet library, complete with the hushed atmosphere that comes with cooler temperatures. The boundary you're exploring extends far beyond what you can see. These thermal layers wrap around the entire planet like invisible blankets, creating a three-dimensional structure that influences everything from whale migration patterns to the path of hurricanes. The warmth trapped in surface layers provides energy for tropical storms, while the cool depths below act like a vast refrigerator, storing cold water that will eventually resurface in distant parts of the world. Ancient mariners unknowingly navigated these temperature boundaries for centuries, noticing that certain areas of the ocean felt different against their skin or produced different weather patterns. They developed folklore about warm and cold currents, not realizing they were observing the surface expressions of this complex thermal architecture that extends thousands of meters below. As you hover between these invisible worlds, you begin to appreciate that temperature in the ocean isn't just about comfort or survival. It's about the fundamental organization of marine life itself, an invisible filing system that sorts and separates different forms of life into their appropriate thermal neighborhoods. Moving deeper through these thermal layers, you encounter something truly extraordinary. Water masses that carry within them the memory of distant places and ancient times. The cool water surrounding you now hasn't seen sunlight for decades, possibly centuries, and it carries with it the chemical signature of wherever it first plunged into the ocean's depths. You are now swimming through what oceanographers call a water mass, a distinct body of water that formed somewhere else entirely, and has been traveling through the deep ocean like a slow-moving river within the sea. The water around you might have started its journey near Antarctica, where brutal polar winds cooled to the surface until it became dense enough to sink, beginning an underwater odyssey that has brought it thousands of miles from home. These traveling water masses maintain their distinct characteristics with remarkable persistence. The water that surrounds you carries the exact temperature and salinity it had when it first sank below the surface years ago, like a message in a bottle that happens to be made of the ocean itself. Scientists can trace these water masses across entire ocean basins by following their unique chemical fingerprints. As you drift along with this ancient current, you realize you're part of what researchers call the global conveyor belt, a worldwide circulation system that moves water between ocean basins over timescales that dwarf human civilization. The water around you is part of a journey that might take 1,000 years to complete, connecting the polar regions with the tropics in a continuous invisible flow. You notice that this deep water carries more than just temperature memories. It's loaded with nutrients that accumulated during its long journey through the depths. Dead marine organisms that have sunk from the surface waters above have dissolved into this traveling water mass, creating a nutrient-rich soup that will eventually resurface somewhere far away, perhaps in an upwelling zone where it will fuel massive blooms of marine life. The boundaries between different water masses create some of the ocean's most stable thermal walls. When Antarctic bottom water meets North Atlantic deep water, they don't mix readily despite flowing alongside each other for thousands of miles. It's like watching two rivers of different colors flowing side by side, maintaining their distinct identities even as they travel together through the ocean's depths. Researchers still argue about exactly how long these water masses can maintain their distinct characteristics. Some studies suggest certain deep water masses have remained unchanged for over 1,000 years, carrying with them climate information from medieval times. Other research indicates that even these stable masses eventually mix and lose their distinct signatures, though the process takes far longer than anyone initially expected. You encounter a particularly fascinating phenomenon as you move along this underwater river. The boundary between your current water mass and the layer above creates what scientists call double diffusion, a process where heat and salt migrate across the boundary at different rates. This creates a staircase-like structure of alternating warm and salty layers, each only a few meters thick but remarkably persistent. The water around you also carries dissolved gases that tell stories of surface conditions from decades past. High oxygen levels indicate that this water mass formed in cold, turbulent seas, where waves mixed air into the water. Low oxygen suggests it originated in warmer, calmer regions, where less atmospheric gas dissolved into the sea. Ancient climate scientists study these deep water masses like underwater ice cores, reading the chemical signatures to understand past ocean conditions. The water surrounding you right now contains information about storms that raged when your grandparents were children, about sea ice conditions from decades ago, about atmospheric chemistry from a world that no longer exists. As you follow this slow-moving underwater river, you pass through regions where it encounters obstacles on the seafloor. Underwater mountain ranges force the water mass to rise and fall, creating internal waves within the ocean that can be hundreds of meters tall, yet remain completely invisible from the surface. It's like discovering that the ocean has its own weather system operating in slow motion, thousands of meters below the waves. The most remarkable aspect of these ancient water masses is their patience. While surface currents rush along at speeds measured in kilometers per day, these deep currents move at a pace that would make a glacier seem hasty. The water around you is traveling at roughly the speed of a very slow walk, taking centuries to complete journeys that surface currents finish in months. You now find yourself at one of the ocean's most dramatic boundaries, where water masses of vastly different temperatures and origins collide in what can only be described as underwater weather fronts. The thermocline you encountered earlier was just the beginning. Here you witness the spectacular meeting zones, where tropical warmth confronts polar cold in battles that have been raging for millennia. The water around you begins to shift and swirl as you approach one of these convergence zones. You can actually see the boundary this time, a shimmering distortion where warm Gulf Stream water meets the cold Labrador Current. The temperature difference is so extreme that it creates visible turbulence, like heat waves rising from summer pavement, except you're witnessing it underwater, and the effect extends for hundreds of kilometers. These meeting zones generate their own unique physics. As the warm, less dense tropical water encounters the cold, heavy polar water, it's forced upward, creating massive underwater mountains of temperature that rise and fall with the rhythm of deep ocean currents. You're essentially swimming through three-dimensional weather patterns that exist entirely beneath the sea surface. The biology around these convergence zones becomes incredibly dynamic. Marine life congregates here like underwater cities, taking advantage of the unique conditions created when different water masses collide. The mixing brings deep nutrients to the surface, while the temperature gradients create perfect hunting grounds for predators who understand these invisible landscape features better than most humans understand their own neighborhoods. You notice that the water temperature around you can change by 10 degrees within the span of a few hundred meters. It's like swimming from a heated pool into an ice bath and back again, except the transitions happen gradually enough that marine life has adapted to use these thermal highways for migration and feeding. Tuna follow these temperature boundaries across entire ocean basins, using them like underwater superhighways. The meeting of different water masses creates what oceanographers call frontal systems, underwater equivalents of the weather fronts that create storms in the atmosphere above. These subsurface fronts can extend from the surface to the ocean floor, creating walls of different water that stretch for thousands of kilometers, yet remain completely invisible to satellites and surface observers. Researchers still argue about whether these convergence zones are becoming more or less stable as global climate patterns shift. Some evidence suggests that warming surface temperatures are intensifying these boundaries, while other data indicates that changing wind patterns might be altering the ancient pathways these water masses have followed for centuries. You observe something fascinating about the chemistry at these convergence zones. Different water masses carry different dissolved minerals, gases, and nutrients, so when they meet, they create unique chemical environments. Some zones become incredibly rich in iron, supporting massive blooms of microscopic marine life, while others develop unusual pH levels that favor completely different types of organisms. The convergence zone you're exploring also generates its own acoustic properties. The mixing of different water masses creates layers with varying sound transmission characteristics, turning these boundaries into underwater sound channels. Whales have learned to use these acoustic highways, timing their songs to travel along these temperature boundaries for maximum communication range. As you follow one of these thermal fronts, you realize you're traveling along what was once thought to be empty ocean, but is actually one of Earth's most biologically productive regions. The collision of different water masses brings deep nutrients to the surface while creating the temperature gradients that many marine species require for successful reproduction and feeding. The scale of these convergence zones becomes apparent as you continue your exploration. Some extend across entire ocean basins, creating temperature boundaries that influence global climate patterns. The Gulf Stream's collision with Arctic waters doesn't just affect local marine life, it helps regulate weather patterns across North America and Europe, making these underwater boundaries crucial components of Earth's climate system. You encounter areas where 3 or more different water masses converge, creating incredibly complex three-dimensional structures of temperature and chemistry. These zones generate their own microclimates within the ocean, supporting unique ecosystems that exist nowhere else on Earth. It's like discovering secret gardens hidden within the sea, visible only to those who understand the ocean's invisible architecture. The persistence of these convergence zones amazes you as you explore further. Despite constantly shifting currents and seasonal changes, many of these boundaries maintain their basic structure for decades or even centuries, creating stable underwater landscapes that marine life can depend on across multiple generations. As you continue exploring these invisible boundaries, you begin to notice that you're not alone in recognizing their importance. The water around you teems with life that has evolved specifically to exploit these temperature walls, turning what might seem like barriers into superhighways for migration, feeding, and reproduction. Schools of tuna cruise along the thermocline like commuters, following a familiar route to work, using the temperature boundary as a navigation guide that spans thousands of miles of otherwise featureless ocean. These fish have learned that the convergence zones you discovered earlier concentrate their favorite prey, small fish and squid that also gather at these underwater intersections where different water masses meet. You watch as a group of dolphins appears, diving repeatedly to specific depths that correspond exactly with temperature boundaries. They're not just playing, they're hunting along these thermal layers, where different types of prey, fish separate themselves according to their temperature preferences. It's like watching predators who have learned to read the ocean's invisible filing system. The most remarkable migrants you encounter are the great whales, who use these temperature boundaries as both navigation aids and feeding grounds during their epic journeys between polar and tropical waters. Humpback whales follow thermoclines that stretch from Alaska to Hawaii, using the temperature gradients like underwater road signs that guide them across thousands of miles of open ocean. Marine biologists have discovered that many species use these boundaries as thermal elevators, riding the temperature layers up and down in the water column to access different types of food or to find optimal conditions for different activities. Some fish spend their days in cool, deep water where they can rest and conserve energy, then rise to warmer surface waters at night to feed. The boundaries themselves create unique ecological niches that support specialized communities of marine life. You notice that certain species of plankton exist only in the narrow zones where different temperature layers meet, thriving in the unique chemical conditions created when waters of different origins mix slowly over time. Researchers still argue about whether climate change is disrupting these biological highways that have existed for millions of years. Some studies suggest that warming surface waters are making thermoclines stronger and more stable, potentially benefiting species that depend on clear temperature boundaries. Other research indicates that changing ocean chemistry might be altering the biological productivity of these convergence zones. You observe something fascinating about the feeding behavior around these boundaries. Many deep-sea creatures make daily vertical migrations, following temperature layers up toward the surface at night to feed, then retreating to cooler depths during the day. This daily movement, called the diel vertical migration, might be the largest animal migration on Earth in terms of biomass, yet it happens entirely along these invisible temperature highways. The reproductive strategies of marine life also revolve around these thermal boundaries. Many species time their breeding to coincide with seasonal changes in thermocline depth and intensity, using temperature cues to coordinate spawning across vast areas of ocean. The boundaries provide not just navigation aids, but also environmental calendars that help marine life time their most crucial life events. You encounter areas where the temperature boundaries create natural nurseries for young marine animals. The unique conditions at convergence zones often provide the perfect combination of food availability and protection that juvenile fish and invertebrates need to survive their vulnerable early stages. These invisible boundaries essentially function as underwater kindergartens for numerous species. Some of the most sophisticated boundary navigation occurs among sea turtles, who use temperature gradients during their transoceanic migrations that can last for decades. Young turtles follow specific thermal corridors that carry them around entire ocean basins, using the temperature boundaries like moving walkways that help transport them to feeding and breeding areas, thousands of miles from where they hatched. The acoustic properties of these boundaries also support marine communication networks. Remember the sound channels from the convergence zones. Many marine mammals have learned to position themselves at specific temperature boundaries, where their calls can travel the greatest distances, with the least energy expenditure. It's like discovering that the ocean has its own internet infrastructure made entirely of temperature differences. As you follow these biological highways through the sea, you realize that the invisible walls you've been exploring aren't just physical features of the ocean, they're fundamental organizing principles that have shaped the evolution and behavior of marine life for millions of years, creating a hidden world of thermal ecology that operates entirely below human perception. As you descend deeper into the ocean's thermal archive, you begin to understand that these temperature boundaries are more than just current features of marine geography. They're living records of Earth's climate history, preserving information about past conditions in layers that extend back through centuries and millennia. The water around you carries within its molecular structure the memory of ancient storms, long-vanished ice ages, and climate patterns that existed before human civilization began recording weather. Each thermal layer represents a different chapter in Earth's climate story, written in the language of temperature, salinity, and dissolved chemicals that only oceanographers know how to read. You encounter water that last touched the surface during the medieval warm period, when Vikings were establishing settlements in Greenland and Europe was experiencing unusually mild temperatures. This ancient water has been slowly circulating through the deep ocean for nearly 1,000 years, carrying with it the chemical signature of that distant era's atmospheric conditions. The precision with which the ocean preserves this climate information astounds researchers who study these deep thermal layers. Unlike ice cores or tree rings, which provide climate records from specific locations, these water masses carry information from vast areas of ocean surface, creating climate records that represent regional and sometimes global conditions from centuries past. As you move through these historical layers, you notice that some boundaries are remarkably sharp and persistent, indicating periods when Earth's climate was stable and consistent. Other zones show evidence of mixing and disruption, suggesting times when dramatic climate shifts occurred rapidly enough to disturb the ocean's normally stable thermal structure. The chemistry preserved in these ancient water masses tells stories of past atmospheric compositions. Water that sank during periods of high atmospheric carbon dioxide carries different dissolved chemical signatures than water that formed during ice ages, when atmospheric greenhouse gas levels were much lower. It's like reading pages from Earth's atmospheric diary, preserved in liquid form. Researchers still argue about exactly how long these climate signals can persist in the deep ocean before mixing erases their distinctive characteristics. Some evidence suggests that the most stable water masses can preserve climate information for up to 1,500 years, while other studies indicate that even deep ocean mixing eventually homogenizes these ancient signals over millennial timescales. You discover that volcanic eruptions from centuries past have also left their marks in these thermal layers. Major volcanic events that altered global climate patterns created water masses with unique chemical signatures that can still be detected today, floating through the deep ocean like liquid time capsules from some of history's most dramatic climate disruptions. The biological implications of these ancient water masses become apparent as you explore further. Many deep-sea organisms have evolved to thrive in water that has remained largely unchanged for centuries, creating ecosystems that are essentially living in ancient oceans. These creatures exist in environmental conditions that might be more similar to medieval seas than to today's surface waters, Ocean paleoclimatologists use these thermal archives to understand how Earth's climate system responds to different types of forcing, whether from volcanic eruptions, solar variability, or changes in atmospheric greenhouse gas concentrations. The water around you contains information about natural climate variability that extends far beyond human historical records. You notice that some of these ancient water masses carry remarkably high levels of dissolved oxygen, indicating they formed in polar regions during particularly cold periods when icy waters could dissolve large amounts of atmospheric gases. These well-oxygenated ancient waters support deep-sea life in regions that might otherwise be too oxygen-poor for complex organisms. The most fascinating aspect of swimming through these climate archives is realizing that the boundaries between different historical periods aren't just temporal, they're spatial, and still exist around you in the present moment. You can literally move from water that formed during the Little Ice Age to water that formed during the medieval warm period, simply by changing your depth or horizontal position in the ocean. Some of the temperature boundaries you've explored represent the interfaces between different climate epochs, zones where water masses from different historical periods meet and slowly mix. These boundary regions contain blended climate signals that help scientists understand how Earth's climate system transitions between different stable states over long time periods. As you contemplate the vast climate library surrounding you, you realize that these ancient water masses are still actively influencing modern climate patterns, bringing centuries-old temperature and chemical conditions back to the surface through upwelling zones and deep water formation processes that continue to shape Earth's climate system. The ocean's thermal architecture reveals its most dynamic characteristic as you witness how these seemingly permanent temperature boundaries shift and transform with the changing seasons, creating an underwater landscape that breathes and pulses with Earth's annual rhythms. During summer months, intense solar heating strengthens the surface thermocline, making the temperature boundaries more pronounced and pushing them deeper into the water column. You observe how the warm surface layer thickens like an expanding blanket, creating more distinct separation between the sun-warmed waters above and the perpetually cool depths below. As autumn arrives, the seasonal transformation becomes dramatic. Storm systems begin breaking down the thermal barriers that seemed so permanent during summer's calm. You watch as powerful waves and wind-driven mixing erode the sharp temperature boundaries, blending layers that had remained separate for months and creating entirely new thermal landscapes in the process. Winter brings the most spectacular changes to these invisible walls. In polar and temperate regions, surface cooling can completely eliminate the summer thermocline, creating nearly uniform temperatures from surface to significant depth. It's like watching the ocean's invisible architecture dissolve and reform, creating temporary thermal highways that connect surface and deep waters in ways impossible during other seasons. The spring renewal of thermal boundaries provides some of nature's most remarkable displays of oceanic reorganization. As surface waters begin warming again, new thermoclines form with almost mathematical precision, rebuilding the layered structure that supports so much marine life. You witness the ocean literally reconstructing its invisible floors and walls from the molecular level upward. These seasonal thermal walls create temporary migration corridors that many marine species depend upon for their annual life cycles. Fish that spend winter in deep, uniformly cool water suddenly find thermal highways opening in spring, allowing them to access rich feeding grounds in newly warmed surface layers without crossing temperature barriers that might stress their physiology. Researchers still argue about whether these seasonal patterns are becoming more extreme or more muted due to climate change. Some regions show evidence of stronger seasonal thermoclines as surface warming intensifies, while other areas appear to be losing their distinct seasonal thermal cycles as overall ocean temperatures rise and weather patterns shift. You notice that these seasonal boundaries don't just appear and disappear uniformly across the ocean. Coastal areas might develop strong seasonal thermoclines, while nearby deeper waters maintain more stable year-round thermal structure. It's like watching different neighborhoods of the ocean follow completely different seasonal schedules. The biological productivity around these seasonal thermal walls creates some of the ocean's most dynamic ecosystems. Spring thermocline formation often triggers massive blooms of microscopic marine life as nutrients from deep water become trapped in newly formed warm surface layers, creating underwater gardens that appear and disappear with seasonal regularity. Some of the most dramatic seasonal thermal walls occur in regions where different ocean currents interact. Remember those convergence zones from earlier. The thermal boundaries can strengthen dramatically during certain seasons and nearly disappear during others, creating temporary underwater mountains and valleys of temperature that migrate across vast areas of ocean. The timing of seasonal thermal wall formation has become crucial for marine life reproduction cycles. Many species have evolved to spawn precisely when seasonal mixing brings nutrients to the surface, but before strong thermoclines form that might separate larvae from their food sources. It's a delicate biological dance timed to match the ocean's seasonal thermal rhythms. You encounter regions where seasonal thermal walls create temporary acoustic channels, underwater sound highways that exist only during certain months of the year. Marine mammals have learned to time long-distance communication to coincide with these seasonal sound corridors, suggesting that even whale culture adapts to the ocean's changing thermal architecture. The most ephemeral of these seasonal boundaries are the ones created by individual storm systems. A powerful hurricane can temporarily destroy thermal barriers that took months to establish, creating short-lived mixing zones where surface and deep waters blend before gradually reorganizing into new thermal layers as the storm passes. As you experience these seasonal transformations, you realize that the ocean's thermal boundaries aren't static features, but dynamic, breathing structures that expand and contract, strengthen and weaken, appear and vanish in response to seasonal changes that connect the ocean to atmospheric patterns thousands of miles away, and climatic cycles that span entire years. Your exploration of the ocean's thermal architecture leads you to discover one of its most remarkable features, the way these temperature boundaries create and channel sound through the depths, turning the sea into a vast acoustic network where whale songs can travel across entire ocean basins. As you position yourself within one of these thermal layers, you begin to hear the ocean's hidden symphony. The same temperature boundaries that separate marine ecosystems also create sound channels, underwater highways, where acoustic waves become trapped and can travel for thousands of miles with remarkably little energy loss. It's like discovering that the ocean has its own fiber optic network, except instead of light, it carries the voices of marine life. The physics behind these acoustic channels emerges from the precise temperature gradients you've been exploring. Sound waves naturally bend toward cooler, denser water, so when they encounter a thermal layer surrounded by warmer water above and below, they become trapped in a channel that acts like an underwater wave guide, focusing acoustic energy and allowing it to travel extraordinary distances. You realize you're floating in what researchers call the so-far channel, the sound fixing and ranging layer that exists at depths where temperature and pressure create perfect conditions for long-distance underwater communication. This natural acoustic highway sits roughly a kilometer below the surface in many parts of the ocean, invisible to the eye but clearly audible to anyone who knows how to listen. The most famous users of these thermal sound channels are the great whales, whose low-frequency calls are perfectly tuned to travel through these acoustic highways. You might be hearing whale songs that originated hundreds or even thousands of miles away, carried to your location by the same temperature boundaries that organize the ocean's vertical structure. Blue whales produce calls at frequencies that propagate most efficiently through these thermal sound channels, suggesting they evolved their communication systems specifically to exploit the ocean's acoustic architecture. Their songs can travel across entire ocean basins, creating a global communication network that connects whale populations separated by vast distances of open sea. Researchers still argue about whether increasing ocean noise from human activities is disrupting these ancient acoustic highways. Ship traffic, seismic surveys, and industrial noise all add sound pollution to the thermal channels that marine life has relied upon for millions of years, potentially breaking communication links that span entire ocean basins. You notice that different thermal layers carry sound with different characteristics. The temperature boundaries you explored earlier don't just separate water masses, they create distinct acoustic zones where sounds behave differently. High frequency clicks and calls that work well in warm surface waters become ineffective in the cool depths, while low-frequency sounds that barely register near the surface can travel for thousands of miles in deep thermal channels. The seasonal thermal walls you witnessed earlier also create temporary acoustic corridors. During winter mixing, when thermal boundaries weaken or disappear, these sound channels can be disrupted, forcing marine animals to adjust their communication strategies. Some whale populations change their calling patterns seasonally, adapting to the changing acoustic landscape created by shifting thermal boundaries. Military researchers discovered these thermal sound channels during World War II, realizing that underwater explosions could be detected across entire ocean basins by listening stations positioned in the SOFAR channel. This discovery revealed that the ocean's thermal structure creates a natural global monitoring system, where sounds from anywhere in the sea can potentially be detected thousands of miles away. You encounter zones where multiple thermal layers create complex acoustic environments with several distinct sound channels operating at different depths. These areas become acoustic crossroads where sounds from different thermal highways intersect, creating underwater regions where you might simultaneously hear whale calls from multiple distant populations. The ancient water masses you explored earlier also carry their own acoustic signatures. Water from different origins has slightly different sound transmission properties, so experienced researchers can sometimes identify the source region of deep water masses simply by analyzing how sounds travel through them. It's like each ancient water mass has its own acoustic fingerprint. The convergence zones where different water masses meet create particularly interesting acoustic environments. Remember those underwater weather fronts? They often generate acoustic boundaries where sound waves can be reflected, refracted, or channeled in unexpected directions, creating acoustic phenomena that marine life has learned to exploit for enhanced communication range. As you listen to this hidden acoustic world, you realize that the temperature boundaries you've been exploring don't just organize marine life spatially, they create a communication network that connects marine ecosystems across vast distances, allowing the ocean's inhabitants to maintain contact across a scale that rivals human telecommunications systems. Your journey through the ocean's thermal architecture reaches its most dramatic moments as you witness the rare instances when these seemingly permanent temperature boundaries collapse, creating spectacular underwater events that can reshape entire marine ecosystems in a matter of days or hours. The first signs of thermal boundary breakdown appear as subtle changes in the water around you. The sharp temperature gradients that have defined your underwater journey begin to blur, and you notice increasing turbulence as different water masses start to mix in ways that contradict everything you've observed about the ocean's stable layered structure. You're about to witness what oceanographers call a mixing event, a phenomenon where the invisible walls you've been exploring suddenly become permeable, allowing waters that have remained separated for decades to blend together in massive underwater storms that occur entirely below the surface. These events can be triggered by powerful deep currents, underwater earthquakes, or extreme weather systems that penetrate deep enough to disrupt the thermal equilibrium. The scale of mixing you observe defies comprehension. Water masses that carried distinct temperature signatures from different centuries begin blending together, creating new hybrid water masses with chemical and thermal properties that haven't existed in the ocean for potentially thousands of years. It's like watching different chapters of climate history being shuffled together and rewritten in real time. Marine life responds to these mixing events with behaviors that suggest they understand the significance of what's happening. Fish that have remained in specific thermal layers suddenly dart across boundaries they've never crossed before, taking advantage of the temporary breakdown in the ocean's thermal architecture to access new feeding grounds or escape from predators. The biological consequences of these mixing events extend far beyond immediate behavioral changes. When deep, nutrient-rich waters mix with surface layers during thermal boundary collapse, they can trigger massive blooms of marine life that are visible even from space. Satellite images sometimes capture these underwater mixing events as sudden green patches in the ocean, where microscopic life explodes in response to the nutrient influx. Researchers still argue about whether these mixing events are becoming more or less frequent as global climate patterns shift. Some evidence suggests that intensifying storms and changing current patterns are increasing the frequency of thermal boundary breakdowns, while other data indicates that overall ocean warming might be making thermal layers more stable and resistant to mixing. You observe that not all mixing events are chaotic disruptions. Some occur with almost rhythmic regularity, suggesting that even the breakdown of thermal boundaries follows patterns that marine life has learned to anticipate and exploit. Certain species appear to time their reproduction or migration to coincide with these predictable mixing cycles. The acoustic effects of thermal boundary collapse create some of the ocean's most dramatic underwater soundscapes. Remember those sound channels created by temperature layers? When thermal boundaries break down, the acoustic highways they supported are suddenly rerouted, creating underwater echoes and sound shadows that can disorient marine animals accustomed to navigating by acoustic landmarks. Some mixing events create entirely new temperature boundaries, as previously separated water masses reorganize themselves according to density. You witness the birth of new thermal layers as the mixed waters sort themselves into fresh patterns, creating temporary underwater landscapes that might persist for months or years before stabilizing into more permanent structures. The chemistry of mixing events produces some fascinating underwater phenomena. When ancient water masses blend with modern surface waters, they create unique chemical environments that can support marine life communities found nowhere else in the ocean. These temporary ecosystems might exist for only weeks or months before the mixed waters redistribute themselves into more stable configurations. Large-scale mixing events can affect ocean circulation patterns far from their origin points. The breakdown of thermal boundaries in one region can alter current flows that influence temperature patterns thousands of miles away, creating cascading effects that eventually circle back to influence the same regions where the original mixing occurred. You encounter areas where partial mixing has created entirely new types of thermal boundaries, hybrid zones where ancient water masses and modern waters exist in complex layered arrangements that don't match any of the classical patterns described in oceanographic textbooks. These transitional zones often support unique biological communities adapted to the unusual thermal conditions. The most spectacular mixing events occur when multiple thermal boundaries collapse simultaneously, creating three-dimensional underwater storms that can extend from surface to seafloor. During these rare events, the ocean's entire thermal structure in affected regions can be completely reorganized, creating new underwater landscapes that might take decades to fully stabilize. As you witness these dramatic breakdowns and reformations of the ocean's invisible architecture, you realize that the thermal boundaries you've explored aren't just stable features of marine geography, but dynamic, evolving structures that occasionally undergo revolutionary changes that reshape the underwater world in ways both dramatic and profound. As your journey through the ocean's invisible architecture draws toward its conclusion, you find yourself contemplating the profound realization that these temperature boundaries you've explored represent one of Earth's most fundamental organizing principles, connecting every drop of water in the sea through an intricate network of thermal relationships that spans the entire planet. The thermal walls you've discovered aren't isolated features existing independently in different parts of the ocean. They're all interconnected components of a single vast system that links polar ice caps with tropical coral reefs, connects surface waters warmed by equatorial sunshine with abyssal depths that haven't seen light for centuries, and ties together marine ecosystems separated by thousands of miles of open sea. You begin to understand that the temperature boundaries create what scientists call the global thermohaline circulation, a planetary scale conveyor belt that moves water, heat, nutrients, and life itself between different regions of Earth's oceans. The ancient water masses you encountered earlier are part of circulation patterns that take over 1,000 years to complete their full circuit, making the ocean's thermal structure a truly global phenomenon that operates on geological timescales. Every thermal boundary you've explored plays a role in regulating Earth's climate system. The warm surface, waters trapped above thermoclines, store vast amounts of solar energy that influences atmospheric weather patterns, while the cold, deep waters serve as enormous reservoirs of carbon dioxide and other gases that help regulate atmospheric composition over centuries and millennia. The seasonal thermal walls you witnessed contribute to regional climate patterns that affect weather systems far inland. The formation and breakdown of coastal thermoclines influences fog formation, precipitation patterns, and seasonal temperature variations that can be detected hundreds of miles from the nearest ocean, demonstrating how these underwater boundaries extend their influence far beyond the sea itself. Marine life throughout the world's oceans has evolved in response to this global network of thermal boundaries. The migration routes of great whales, the spawning cycles of countless fish species, the distribution patterns of marine ecosystems, and even the evolution of different body forms and physiological adaptations all reflect millions of years of adaptation to the ocean's thermal architecture. Researchers still argue about how human activities are affecting this global thermal system. Climate change is altering the strength and position of thermal boundaries worldwide, potentially disrupting circulation patterns that have remained stable for thousands of years. Some evidence suggests these changes are happening faster than marine ecosystems can adapt, while other research indicates that life in the oceans has survived similar disruptions in the geological past. The acoustic highways created by thermal boundaries form a communication network that spans the entire planet, allowing whale songs recorded in the Pacific to be detected by listening stations in the Atlantic through acoustic channels that follow the same thermal boundaries you've explored. This global underwater internet predates human telecommunications by millions of years and continues to operate with remarkable efficiency. The chemical signatures preserved in thermal boundaries create a worldwide archive of environmental information that helps scientists understand not just past climate conditions, but also the current health of marine ecosystems. Changes in the chemistry of thermal boundaries can indicate alterations in atmospheric composition, ocean productivity, and ecosystem function that might not be detectable through any other means. You realize that the invisible walls separating different water masses are simultaneously barriers and bridges, preventing some forms of mixing while enabling others, creating both isolation that allows distinct ecosystems to develop and connections that link all parts of the ocean into a single integrated system that has been operating continuously for millions of years. The convergence zones, where different thermal boundaries meet, serve as crucial transfer points in the global system, regions where waters from different ocean basins exchange heat, chemicals, and biological material. These underwater crossroads help maintain the ocean's role as Earth's primary climate regulator and its largest habitat for life. As you prepare to conclude your exploration of this invisible underwater world, you're struck by the realization that these temperature boundaries represent one of nature's most elegant solutions to the problem of organizing vast, three-dimensional spaces. Through nothing more than subtle differences in their heat content, the ocean has created a complex, stable, and remarkably persistent architecture that supports the majority of life on Earth. The thermal boundaries you've discovered don't just organize the ocean, they help organize the entire planet, connecting atmospheric and oceanic systems, linking biological and geological processes, and maintaining the delicate balance of conditions that makes Earth habitable for millions of species, including the humans who are only just beginning to understand and appreciate this magnificent invisible world. And so, As your journey through the ocean's hidden thermal architecture comes to a gentle close, you find yourself floating peacefully in these layered waters, surrounded by invisible walls that have existed since long before humans walked the earth, and will continue their silent work long after we're gone. The boundaries you've explored tonight aren't just scientific curiosities, they're the quiet guardians of our planet's climate, the unseen organizers of marine life, and the gentle architects of an underwater world far more complex and beautiful than most people ever imagine. Every thermocline, every convergence zone, every ancient water mass contributes to the vast, slow breathing of the ocean that helps keep our entire planet in balance. As you drift through these temperature layers one final time, you can appreciate how each invisible wall tells a story, carries a memory, supports a community of life. The warm surface waters above hold the energy of today's sunshine, while the ancient depths below carry the chemical whispers of centuries past. Between them, these thermal boundaries create the structure that allows both to coexist in the same vast sea. The ocean's invisible architecture will continue its patient work through the night, moving nutrients from deep to shallow, carrying whale songs across vast distances, preserving climate records in its layered depths, and maintaining the thermal balance that makes life possible throughout the sea. These temperature boundaries are always there, always working, always organizing the underwater world with gentle precision. So rest now, knowing that somewhere beneath the waves, these invisible walls continue their ancient dance, separating and connecting, preserving and mixing, maintaining the delicate thermal balance that keeps our blue planet spinning peacefully through space. The ocean's hidden architecture surrounds every coastline, influences every weather pattern, and touches every life on Earth, working its quiet magic in the depths, while we sleep safely on the surface above. Sweet dreams knowing that the ocean's invisible walls are always there, always working, always keeping watch over our beautiful, complex, perfectly organized blue world. End of script. Sweet dreams.